Strings, pulleys, and gravity. There are many situations where the gravitational force acting on one object indirectly produces motion in another object. In some cases, a falling object is connected to another object by a light string or rope passing over a nearly frictionless pulley. When we're dealing with strings and pulleys, we're going to make a few assumptions. The first is strings are considered to have negligible mass. That means we're not going to worry about how heavy they are, and they're capable of exerting only pulling forces on the object. They can't push. If they could push, they'd be considered a stick, not a string. And when they pull, these are what we call the tension forces. So strings transmit forces undiminished. The tension force in the string is the same throughout its length. So it doesn't matter if we have a short string or a long string, the tension is going to be the same everywhere. A frictionless pulley changes the direction of the string without diminishing its tension. So all a pulley does is it allows us to, say, pull in one direction and drag an object in a different direction. Also, strings are assumed not to stretch. If they did stretch, they wouldn't be strings at all. They'd be considered elastics. A 2-kilogram mass is attached by a long string passing over a frictionless pulley to a 5-kilogram mass hanging over the edge of a table. If the coefficient of kinetic friction is 0.1, so that's our mu, what is A, the tension in the string, and B, the acceleration of the 2-kilogram mass? So we have this mass, here's our string, this one's just hanging. The first thing you do is you always draw your free body diagram for each object. So the first one is a 2-kilogram mass, and the other one is a 5-kilogram mass. We're going to draw all our forces on here. So this object is moving to the side because of the string. So it's moving over because of the force of tension. So I'm going to draw that in. So I have force of tension going to the right. I don't know what that is. What's preventing it from moving is the force of friction. Friction is always in the opposite direction that we're traveling. So we know the force of friction is equal to mu times the force of normal. And we can calculate what that is. So mu in this case here is 0.1. The normal, because it's just on a flat surface, is equal to mg. So it'll be 2 times g, which is 9.8. And I end up with 1.96. Our other mass is hanging. So what's pulling it down is the force of gravity. So we have the force of gravity is equal to mg. So that would be 5 times 9.8, which gives me 49 newtons. Preventing this object from free falling down is the tension in the string. So we have the force of tension, and we don't know what that is. So first thing you do, like I said, is you draw your free body diagrams for each object. Now what we're going to do is we're going to write out our Fnet formulas for each of them. So in this one here, I know that Fnet is equal to ma, which is equal to the sum of the forces. Now, you know you're always going to write the bigger one first. And this object's moving to the right. That means tension is bigger than friction. So I'm going to write down the force of tension minus the force of friction. The minus is because they're in opposite directions. This one's going to the right, this one's going to the left. And we'll plug in what we know. So the mass is 2a is equal to the force of tension minus the force of friction, which is 0.96. We're going to do the same thing for the other mass. So we have Fnet is equal to ma is equal to the sum of the forces. So in this case here, this object's moving down, so the force of gravity is bigger than the force of tension. So it's going to be the force of gravity subtract the force of tension. It's negative because we're in the opposite direction. Plug in what we know, which will be 5a is equal to 49 minus the force of tension. Now we have a math problem. We have 2 equations and 2 unknowns. I like solving this one for one of the variables and then plugging it into the other ones. We call that substitution in math, but there's more than one way to do this. So I'm just going to do it the way I like it. To get ft all by itself, I have ft minus 1.96. So if I add 1.96 to both sides, it actually disappears. And I have ft all alone. So I have ft is equal to 2a plus 1.96. Now what I'm going to do is wherever I see an ft, this is my ft in the other formula, I'm going to plug that in. That's why we call this substitution. I'm substituting this in for ft. So let's write it out. I'm going to continue to solve over here. So I have 5a is equal to 49 minus, and I usually just put it in brackets so I don't mess up my signs at all. It's 2a plus 1.96. I need to expand the bracket by multiplying both by the negative. So I get 5a is equal to 49 minus 2a minus 1.96. To get the 2a onto the other side, I'm just going to add it to both sides. So I end up with 5a plus 2a is 7a. 49 minus 1.96 gives me 47.04. And then finally, to get a all by itself, I'm going to divide both sides by 7. I get 6.72 meters per second squared. So I've solved for the acceleration. But the question also wanted to know what the tension in the string is. All I need to do is take this A and I can plug it into either this formula or this formula, and then I can solve for tension. This one's already been rearranged for the tension for it, so it's just a little easier for me to use. So I'm going to use that one. So I know force of tension is equal to 2a plus 1.96. Plug in my A, which is 6.72. So it'll be 2 times 6.72 plus 1.96. I put that into my calculator. Plus 1.96. And I get 15.4 is my answer.